Welcome to this video on 4-node quadrilateral elements. This is one of several videos in a short course on the finite element method posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. It is helpful to learn the computational stiffness method as a foundation for learning the finite element method. However, it is only with the consideration of an element like the 4-node quadrilateral element, shown here, that we get exposed to the full-fledged finite element method. Not only does the finite element method for this element give us solutions that we could not find in other ways, we also get exposed to concepts like two-dimensional shape functions, the isoparametric formulation, integral transformation, numerical integration, and the consistent load vector. Those are topics addressed in this video. There are several element types that would be suitable for the learning of such concepts, but it is the so-called Quad4 element that is employed in this video. It is an element that carries load only in its own plane. It has 4 nodes, with 2 displacement degrees of freedom at each node. This element has many potential applications. A shear wall in a building can be discretized into many Quad4 elements, as can a hydro dam. The fact that each element can have any shape is an important point addressed in subsequent slides. Notice that we are working in the XY coordinate system in this video. The boundary value problem is essentially the two-dimensional theory of elasticity. It is here visualized in a generic manner, matching the pattern of figures that appear many places in terje's toolbox. Equilibrium is on the left, kinematic compatibility is on the right, and material law is at the bottom. Notice that equilibrium and the differential equation are gray shaded in this slide. That is because we do not enforce equilibrium at every point of an element in the finite element method. In other words, we do not solve the differential equation to get an exact solution. Instead, we use the principle of virtual displacements, that is, the weak form of the boundary value problem, which expresses equilibrium only on average over the element. The next slide shows that the external forces, in this case, are expressed in a vector, P, of distributed loads. Px is the distributed load over the element, or its edges, in the x direction. Py is the distributed load in the y direction. The stresses in the element include axial stress and shear stress. Sigma x is the axial stress in the x direction. Sigma y is the axial stress in the y direction, and tau xy is the shear stress at some point in the element. In the same manner, the strains in the element include axial strain and shear strain. Epsilon x is the axial strain in the x direction. Epsilon y is the axial strain in the y direction, and gamma xy is the shear strain. The displacement vector has 2 components. U is the displacement in the x direction anywhere in the element. V is the displacement in the y direction anywhere in the element. Notice the tilde that is introduced in order to avoid confusion with the vector of degrees of freedom, also denoted U, which is an entirely different entity. U tilde is a vector of displacements at any point in the element. Conversely, U is a vector of degrees of freedom. The next slide shows the procedure to derive the stiffness matrix and load vector by the finite element method. We saw this procedure carried out for truss and beam elements in another video in this short course on the finite element method. The starting point is the principle of virtual displacements, which is the weak form of the boundary value problem. Next, we substitute material law and kinematic compatibility. Remember, the principle of virtual displacements does by itself represent an average satisfaction of equilibrium. Then, we introduce the discretization of the displacement anywhere in the element by means of shape functions and degrees of freedom. Finally, by carrying out the integrals that stem from the principle of virtual work, we obtain the stiffness matrix and the load vector. The next slide starts this process by first spelling out the principle of virtual displacements. Virtual strains are multiplied by real stress and integrated over the volume of the element. In the other term, virtual displacements anywhere in the element are multiplied by the real distributed loads. The material law is expressed in terms of a matrix, D, because the stress and strain are vectors. We know from the document on two-dimensional theory of elasticity posted at terje.civil.ubc.ca Toolbox that the material law comes in two versions. The so-called plane stress material law is shown at the top on the right-hand side. The plane strain material law is shown below. Plane stress applies when there are no stresses perpendicular to the considered plane. This applies to relatively thin planar members, such as a wall or a narrow beam that is modeled with two-dimensional continuum elements. Seen from the side, such a beam forms a two-dimensional continuum problem in the xz plane. The plane stress material law is appropriate in this case because there is no stress perpendicular to the sides of the beam. Conversely, plane strain implies that there is zero strain perpendicular to the plane under consideration. This applies to problems where the plane is a cross-section of a structure that is long in the direction perpendicular to that plane. One example is the modeling of the cross-section of a hydro dam, shown earlier in this video. From the selected cross-section, the dam stretches out to both sides until it meets mountainside supports. This restrains displacement, and hence strain, perpendicular to the plane that we saw in that earlier slide. That plane is then in a state of plane strain, without strain perpendicular to it. The equation at the bottom of this slide shows the material law substituted into the principle of virtual displacements. The next slide shows the kinematic compatibility relationship between strains and displacements, also taken from the two-dimensional theory of elasticity. The equations for axial strains are well known. Those equations say that the axial strain in a specific direction is the derivative of the displacement in that direction. That is the definition expressed as change in length over original length that we use in any basic structural analysis. However, those equations are now expressed in matrix form. The shear strain expression derived in the two-dimensional theory of elasticity says that gamma is the derivative of the displacement in the x direction with respect to y, plus the derivative of the displacement in the y direction with respect to x. Carefully note that we have introduced the symbol nabla to represent the matrix of differential operators. Next, we introduce the fundamental equation of the finite element method, which discretizes the displacement fields. The displacement anywhere is expressed as a matrix of shape functions times the vector of degrees of freedom. In this case, there are 8 degrees of freedom in the element, so we need 8 shape functions. However, we will soon see that some of them are identical, so only 4 shape functions will be formulated. One for each of the 4 nodes. We now substitute the shape function discretization into the kinematic compatibility equation. At the top of the slide, that equation said that strains are equal to nabla times u tilde. It now says that the strains are equal to nabla times the n matrix times the u vector of degrees of freedom. Importantly, we denote the product of the nabla matrix and the n matrix by the symbol B, which is shown on the right-hand side. The B matrix is a staple of the finite element method for two-dimensional and three-dimensional elements. Any textbook on the finite element method will explain the B matrix, probably using exactly that symbol. The B matrix is essentially the kinematic compatibility relationship between strains and degrees of freedom. Strains are equal to B times U. For subsequent slides, it is helpful to remember that the B matrix contains the derivative of shape functions with respect to the x and y coordinates. That will become a significant fact, because we will not formulate the shape functions in the xy coordinate system. For now, we proceed down this slide by substituting that new kinematic compatibility equation into the principle of virtual displacements. Notice that when we resolve the parenthesis that has a transpose, we switch the order of multiplication of b and delta u. Furthermore, we pull the virtual displacements, delta u, outside the integrals. Next, we recognize that the only way for this expression to be 0 is for the outer parenthesis to be 0, because the virtual displacements, delta u, are arbitrary. That leads to the equation at the bottom, which shows that we have now derived integral expressions for the stiffness matrix and the load vector for the element. This is a major contribution of the finite element method. However, we have several steps to take before we can actually evaluate these integrals. First on the agenda is the formulation of the shape functions, which is addressed on the next slide. Because the element can have any shape, it is awkward to formulate the shape functions in the xy coordinate system. This is why we will formulate the shape functions for a square template element in the Eta coordinate system. The element spans from -1 to 1 along both axes. This template element will be transformed into actual elements of any shape. A shape function in the finite element method has the following characteristics. It must be equal to unity at the degree of freedom it is associated with. Also, it must be equal to 0 at all other degrees of freedom. Let us exemplify that for degree of freedom number 1. The associated shape function is sketched on the right-hand side. It is indeed equal to 1 at degree of freedom number 1 and equal to 0 at all other nodes. Remember, this sketch shows the amount of x displacement in the element caused by unit displacement along the first degree of freedom. We understand that the shape function is identical for the second degree of freedom. That is because the sketch on the right-hand side also shows the amount of y displacement in the element caused by a unit displacement along the second degree of freedom. This is the reason why we need only 4 shape functions, 1 for each node. The equations below show the mathematical expressions for those 4 shape functions. The first, n1, is sketched above. The equation on the left-hand side highlights that we have 8 degrees of freedom but 4 shape functions. Notice how the u displacement anywhere in the element is expressed by n1 times u1, n2 times u3, n3 times u5, and n4 times u7. Also notice that the shape functions are expressed in terms of xi and eta, while the previous expression for the stiffness matrix and load vector was an integral in the xy coordinate system. The next slide addresses that point. Integral transformation is a concept in calculus which says that we can carry out the integration in another coordinate system if we multiply the integrand by the so-called Jacobian. The Jacobian is the ratio of differentials in the two-coordinate system. The one-dimensional integral is given at the top of this slide as an introduction. The integral of the function f of x along the x-axis can be carried out along the xi axis if we substitute the equation for x in terms of xi in the integrand and multiply by the ratio of differentials, dx over d xi. For this to be possible, we must define the relationship between the two variables x and xi, and that will be addressed in this video. First, we examine the two-dimensional case. When we transform an integral in the xy plane into an integral in the xi eta plane, it is necessary to multiply the integrand with the determinant of the Jacobian matrix shown below. The Jacobian matrix contains all the ratios of differentials in the two coordinate systems. In the bottom equation, we apply this concept to the integral of the stiffness matrix. Instead of the volume integral we saw earlier, this is now an integral between -1 and 1 in the xi eta plane. We have multiplied by the thickness of the element, denoted by h, in order to carry out the integration in the direction perpendicular to the plane. Notice the appearance of the Jacobian. Also, remember that the B matrix contains derivatives with respect to x and y, while the shape functions are formulated in terms of xi and eta. That issue is addressed on the next slide by means of the chain rule of differentiation. The derivative of a shape function, n, with respect to x is dn, d xi times d xi, dx, plus dn, d eta times d eta, dx. The differentiation with respect to y follows the same pattern. The derivatives d xi, dx, etc. are the inverse of the Jacobian entries we introduced on the previous slide. For that reason, the derivatives needed on this slide are taken directly from the inverse of the Jacobian matrix, shown below. We have not yet calculated the components of the Jacobian matrix, and that is addressed on the next slide. In order to calculate the ratio of differentials in two coordinate systems, we need a relationship between the coordinate systems. This is an innovation in the finite element method, whereby we use the same shape functions that we used to describe the displacement to now describe the shape of the element. It is the fact that we use the same shape functions that gives rise to the term isoparametric. The equation at the top of this slide shows how this is done. The x-coordinate of any point in the element is a function of the x-coordinate of all the 4 nodes, x1 to x4. Similarly, the y-coordinate of any point in the element is a function of the y-coordinate of all the 4 nodes, y1 to y4. It is those two equations that allow us to determine the derivative of x with respect to xi, etc., for the Jacobian matrix. Those derivatives are shown below. This is simply a matter of differentiating the equations above with respect to xi and eta, which implies differentiating the shape functions in those expressions. This concludes the evaluation of the integrand, but not the integral for the stiffness matrix. For arbitrary element shapes, it is not possible to evaluate the integral analytically. That is why numerical integration, namely quadrature, is needed. The next slide introduces quadrature by first considering a one-dimensional integral. Instead of evaluating the integral, we evaluate a sum. The sum is over integration weights multiplied by the integrand evaluated at certain integration points. Several numerical integration schemes are available, including Gauss integration. The different schemes differ only in their specification of the integration weights and the location of the integration points. Two-point Gauss integration is shown in this figure. The location of the integration points are 0.577 away from the origin of the coordinate system. In this case, the integration weights are equal to 1. This two-dimensional quadrature is spelled out in the expression for the stiffness matrix below. Notice the double sum, and remember that we evaluate the integrand in the parenthesis only at the 4 integration points in the figure above. It is rarely possible to obtain exact results with numerical integration. In addition to the use of shape functions that may not be exact representations of the displacements, the use of quadrature is another source of inaccuracy in the finite element method. For example, Gauss integration provides exact results for integration of polynomials up to order 2n-1, where n is the number of integration points in one direction. The phrase full integration is defined as the integration rule that gives exact results for an undistorted element. Reduced integration is anything less than full integration. Apart from reduction in computational cost, reduced integration is sometimes helpful because it makes the element softer, which counteracts the fact that elements are made too stiff by the assumption of inexact shape functions. On the other hand, the quadrature order must not be so low that the volume of the element is incorrectly computed. This has to do with retaining the convergence properties of the element. The element must be able to capture the constant strain state exactly. Reduced integration may also cause unwanted mechanisms. A mechanism is a deformation mode associated with zero stiffness. Other names for a mechanism in this context are zero energy mode and hourglass mode. These may cause mesh instability, namely global modes of deformation with artificially low stiffness. In other words, a structure may appear adequately restrained by boundary conditions, but may have modes of deformation with very little stiffness. Element mechanisms are detected by performing an eigenvalue analysis of the stiffness matrix, which reveals the number of zero energy modes of the element. The final slide addresses the load vector. It is only for some elements that it is possible to lump distributed element loads as concentrated nodal loads according to tributary areas. In general, we must evaluate an integral, giving what we call the consistent load vector. The integral at the top of this slide is taken directly from the principle of virtual displacements, derived earlier in this video. We first decide that we want to address loads on an edge of the element, denoted by capital gamma. In this example, that is the edge where xi is equal to -1. Next, we transform the integral into the normalized domain, in this case along the eta axis, to address the load on the edge that is parallel to that axis. Notice again the appearance of the Jacobian ratio of differentials. In order to evaluate this Jacobian, we first express the differential of the gamma coordinate along the edge in terms of the differential of the x and y coordinates. With reference to the figure on the right-hand side, this is done by formulating the Pythagoras formula for the triangle shown there. We now need the relationship between the differentials dx and dy and d eta. That is done below. dx is the Jacobian times d eta. Similarly, dy is the Jacobian times d eta. We do not need to consider xi, because xi is not a variable but equal to -1 along the loaded edge. Substituting those two equations into the Pythagoras formula above yields the expression at the bottom, from which the required Jacobian d gamma, d eta is readily available. That concludes this video on the Quad4 element. This has included the exposure to many of the rather theoretical concepts that can be challenging to grasp the first time you encounter the finite element method. Remember, that method is all about obtaining the stiffness matrix and load vector of an element by integration. For elements like the Quad4, this involves shape functions in a normalized coordinate system, integral transformations, the isoparametric description of the shape of the element, evaluation of the Jacobian matrix and its inverse, numerical integration, and evaluation of consistent load vectors. When you understand those concepts, and when you realize that approximate shape functions make the element too stiff, while numerical integration can soften it, you are well on your way to be a finite element expert. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.